Good morning, everyone, and welcome to this last session on the quiz and closing. So this is the last session, the webinar 12, and I hope that for the past 2 weeks you have really enjoyed and learned a lot on statistics and modeling. So this is just the wrap up of the agenda. So today we are the last day together, and we will be together for around 2 hours, where I will start with the quiz on statistics. Then Arnaud will do the quiz on modeling, and then we will have some closing remarks. So now let's get connected to www.menti.com. So I will share my screen. Let me know if you see my screen. So yes, so please connect to www.menti.com and use the code that appears on the screen, which is 68 17 19 64. So I'll give you a few seconds to connect to the tool Menti and use the code 68 17 19 and 64. And the first question is, what do we include in national energy statistics and balances? Do you include the amounts of natural gas used for heating, solar energy reaching the earth, methane emitted while mining coal, fuel wood burned for cooking, electricity used while traveling abroad, or natural gas used as ammonia feedstock? So here you have the several right answers. So you can give several good answers. So among those 6 options, what do we include in national energy statistics and balances? So I'll give you some time to reply to this one. So what do we include? So there are several good answers. We have several good answers arriving. Excellent. So let's look at the right answers. So the right answers here is indeed, we include in national energy statistics and balances the natural gas used for heating, the fuel wood burned for cooking, and natural gas used as ammonia feedstock. So here there was 3 right answers, and most of you got it right. It was the majority. So we include in national energy statistics and balances natural gas used for heating, fuel wood burned for cooking, and natural gas used as ammonia. And here it's very important to keep in mind a few key concepts on the scope and boundaries of energy statistics. And here we have the manual on the International Recommendation on Energy Statistics from the United Nations, where we have we really have the correct definitions for energy products, flows, the energy sector, which territory do we need to take into account. So I really recommend you to take a look at this manual from the UN, and this is what we follow as guideline in the energy balances when we build it up. So next question is, what is an example of how wood is used in energy statistics? So here you have several options. Do you think that we include wood used as material for making furniture, wood used for burning, for home heating, or wood residues burned in a landfill, or none of these? So what is an example of how wood is used in energy statistics? So what do you include? What usage of wood do you include? So I'll give you some time. So most of you got it right. And the correct answer is indeed, in the energy statistics, we include the amount of wood used for home heating. And we don't include wood used as material for making furniture or wood residues burned in a landfill. And this is because only the amounts of specifically used for energy purposes, which is a very small part of the total for solid biofuels, are included in energy statistics. So this is very important to keep in mind when building your energy balances, especially in countries where solid biofuels is a big share of the energy mix. Next question. So which renewable energy source do you think takes the largest portion of global electricity production? So here, which of the three renewable energy source below, so hydro, solid biofuels, or solar photovoltaic, which of these takes the largest portion of global electricity production? So at the world level, which of these renewable sources accounts for the largest share of the global electricity production? So here, this is excellent, as all of you are getting it right. And the correct answer is indeed hydro. And in 2018, hydro accounted for nearly 16% of the total electricity generation by source, and non-hydro renewable and waste, such as solar PV, wind, all the others aggregated together, accounted for a bit less than 10%. Next question. So what is the largest energy consuming sector in the world? Is it the residential sector, the transport sector, or industry sector? So at the world level, which sector do you think consumes the most energy? In situation, things have been a bit different, but think mostly of prior to the pandemic. What do you think was the largest energy consuming sector in the world? So here, all of you replied industry, And the correct answer is both transport and industry, because in 2018, transport and industry both had more or less exactly the same share, 29% of total final consumption. So both industry and transport at the world level are very close in terms of share. But in Africa, what is the largest energy consuming sector? So before we were looking at the world, at the global level, but in Africa, which sector do you think consumes the most energy? So here, most of you are replying residential. Two candidates replied transport. None of you think it's industry. And indeed, the right answer is residential sector. And in Africa, the residential sector consume more than half of the total final consumption. And industry accounts for 16%, transport 20%. So it's really the residential sector that is the biggest consumer of energy. Next question. So which of these regions has the highest share of renewable energy? And here when we say renewable energy, we are also including the traditional use of biomass in their total energy supply. So which of these regions, so Asia, Latin America, or Africa, has the highest share of renewable energy in their total energy supply? And here we are including both modern energy, but also traditional use of biomass. So the majority replied Africa. A few of you replied Asia. None replied Latin America. Let's look at the correct answer. And here, indeed, the correct answer is Africa. Africa is the region that has the highest share of renewable energy in their total energy supply. And if we look at the stats on this, indeed, Africa, it's 47%, followed by Latin America, and then followed by non-OECD Asia, excluding China. And here, when we see this 47%, more than 90% here, it's solid biofuels. So this is an extract of an energy balance for Nigeria. So you are seeing only the top part of it, of the energy balance. And here we ask you to look at this energy balance and tell us if the country is an energy producer, and if so, of what products. So here we are asking you to study this extract of the energy balance for Nigeria and write down for which products do you think Nigeria is an energy producer. Here, think not only in terms of primary products, think also of secondary products, and try to think when we had the balances presentation, how to read an energy balance. So where are primary production reported, where are secondary production reported. So here you have to write down your answer. It's an open-ended question. Let me see if, so someone already replied, yes, it's producing natural gas. Someone says crude oil. Let me show you again the image. So where would production of Nigeria appear in the energy balance? So let me see again. We have a few good answers. Yes, crude oil producer, coal, crude oil, natural gas, hydro, waste, coal, crude oil, oil products. So very good. Many of you. So all of you said yes, this country is an energy producer. Let me show you again the image. So here, where would we look for primary production? So for here we see that Nigeria produces a little bit of coal, a lot of crude oil. Most of this crude oil is exported. Then it also produces quite a lot of natural gas, a lot of biofuels and waste, some hydro, a bit of geothermal, solar, etc. These are the first row here, it's primary production. Then you have secondary products, and those appear lower here in the transformation sector. For example, you have some crude oil that is refined and produces oil products. So here, this is another production, oil products. So it doesn't appear in the production row up, but below. And you also have some electricity produced from natural gas, hydro, geothermal, solar, etc. So you also have some electricity production. Let me see. Yes, so someone replied in the Q&A box, but please try to use Menti so that we have all the answers together and we can really discuss those. So next question now. So this is the bottom part of the energy balance where we will look at the final consumption sector. So again, for Nigeria, look at this energy balance extract and tell us what is the largest final consumption sector. So here, if you look at the table, you see you have the total final consumption, then it's broken down by subsectors. So industry, transport, other here includes residential, services. There's also the non-energy use, such as feedstock, petrochemical. So here, which sector for Nigeria is the largest? Is it industry, transport, other? So try to read this energy balance. So we have a few answers coming in. So yes, so some replied transport, some is saying other. Let's look again at the image here. So where will you look at this? I'll give you some tips here. So here, look at the total, because we are not focusing on the products here, on those energy sources. We are looking at the total sector consumption. So how much is industry consuming? How much is transport consuming? How much is the other sector consuming? And in other sector, you have residential, which consumes a lot as well. So here, it's 50-50, but the correct answer is other. And in other, it's the residential sector, because here, other sector consumes 106,400 something KTOE. And industry consumes only around 7,000, it transports 17,000. So the other sector, and in other sector, it's the residential sector that is consuming more than 100,000 KTOE of energy. So next question, again, we are focusing on the energy balance. It's really, we put a lot of question on energy balances here because we really want everyone to be comfortable and at ease reading and understanding and energy balance, because it's really important to know and make a good policy decision based on good data. So here the question is, what is the difference between a negative number and a positive number in the transformation sector? So the transformation sector is what we have put in the red rectangle here on the table. So here you have some signs. So what is the sign convention here? Maybe we can take an example of a row. For example, oil refineries. You have a negative number for crude oil, you have a positive number for oil products. And then in the total column, you have also a negative number. So what does all these signs mean here? Just write it down. So a negative number represents an input, positive number indicates an output. So we have some good answers arriving. Exactly, is a resource consumed to produce. Positive is a new product generated. Yes. But what about the total column? What does the negative number here, for example, in oil refineries row, what does this minus 396 mean? Same for electricity plants, you have some negative numbers. So very good. So everyone seems to have understood that a negative number here means an input, and a positive number, it's an output of the transformation process. But then what is interesting in the energy balance with the total column is that you can calculate the efficiency of the transformation. And here the negative sign in the total column represents the losses of the transformation. So here you have more input, you have a bit less output. You can calculate, you have the amount of losses, you can calculate the efficiency of the transformation process. Let's look at the next question. So here it's a bit of some guessing to do. So the question is, which country's energy balance is shown below? So here we have removed the name of the country, but we are showing you an extract of an energy balance for a country. And we want you to try to guess which country energy balance this could be. And you have some three options. Is it Algeria, Ethiopia, or France? So among the three countries, which country do you think this is? And I will show you again the energy balance and try to see a bit how the energy mix is here, and try to see if, do you think this is Algeria, is it Ethiopia, or is it France? So I give you some time to study this energy balance and let us know. So 2 participants said Algeria, 4 think that it is Ethiopia. No one said France for the moment. So look a bit at the energy supply, look a bit at the transformation sector as well. How is electricity produced? So two think that it is Syria, Ethiopia, and the correct answer is indeed Ethiopia. And let's see why. If we look at this energy balance, first, why is it not Algeria? So think about Algeria. Algeria is one of the biggest producers of oil and natural gas. And here the production rate is 0. So this is This is not possible for Algeria, which is a big producer of oil and natural gas. And for France, why is it not France? So in France, nuclear plays a big role in electricity production. So here there is no nuclear. And in France, nuclear accounts for more than 70% of its electricity generation. And in this table, nuclear is 0, so we eliminate France. And Ethiopia, why is it Ethiopia and not another country in Africa, for example? So here you have a big biofuels and waste production. So bioenergy is a big share of the total energy supply. And another specificity of Ethiopia is that hydro plays a big role in electricity generation. Most of Ethiopia's electricity mix is made of hydro, and very little from other renewables and very, very little from oil products. So it's more than 90% made of hydro. Next question now. So Africa accounts for what share of global CO2 emissions? Is it less than 5%, between 5 and 10%, more than 10%? So think about global CO2 emissions and what's Africa share in the global scope for emissions. When we were doing the CO2 emissions session, there was a slide on this where we explain. So most of you think less than 5%. 2 participants said between 5 and 10. And here the correct answer is indeed less than 5%. And if we look at the data here, in 2018, Africa accounted for less than 4%. It's 3.7% of the global CO2 emissions. So another question. So what percentage of global CO2 emissions from fuel combustion in 2018 comes from coal? So if you think about global CO2 emissions, what is the share of coal? Is it 35%, 45%, 55%? So emissions from fuel combustions, which is coal, oil, and natural gas, a bit of waste. So what is the share of coal here? So many think that it is more than half, so 55%. If you said 45% and no one said 35, and the correct answer is 45%. And if we look at the share of global CO2 emissions by source, so coal accounted for 44%, oil accounted for 34%, and natural gas for 21%. And the other here, it's non-renewable waste. Next question, which is also the last one on statistics. So countries representing approximately what percentage of the global CO2 emissions from fuel combustion have already pledged net zero emissions targets? Is it 25%, around 50%, or 75%? So what is the share of countries that have pledged net zero emissions? And what's the share of those countries in the global CO2 emissions from fuel combustion. Here we need, so here it's those that have already pledged. So we have countries like the US that had pledged and then got out, and that normally should get in again in the Paris Agreement, but here we are not counting the US. So is it, most of you think it's around 50 and 75%. And here the correct answer, it's around 50. And this is the share of the countries that have pledged. And indeed here it's around 50, but we are excluding the United States. But when we will add again the United States in the list of countries that have already pledged, it will be around 65%. But for the moment, without US, it's around 50. So thank you very much for participating in the statistics quiz. Now I will pass over to Arnaud, who will continue with the modeling part. If you have any questions, yeah, maybe if there are some questions on the statistics part, you can let me know in the Q&A box, and we can take a few minutes to reply to questions if any of you have anything to say. And of course, even after the training, you can always write to us, to me on the statistics questions, to Arnaud, and stay in touch in case you have any questions, clarifications on the content of the training. Do not hesitate. I don't see any questions in the Q&A box, but yes, do not hesitate to drop me questions during the session today.
Okay, so as you might have some questions for Zakia now, in the meantime I propose to start the second part of the quiz on modeling. Maybe Zakia, I see one question on statistics. Maybe we can take it now.
Yes, so there's a question about statistical differences. So statistical differences, it's when your demand and your supply, it's not balancing. There's no equilibrium between your demand and your supply, but in an energy balance, everything has to balance, your demand and your supply. And we have this raw statistical difference where we put this difference when how much you have in the market is not matching how much you're consuming. And some countries, they use the statistical difference sometimes to hide some numbers, some confidential numbers. Sometimes it's because you are not doing a complete survey in the consumption sector, so you're not capturing all your consumption, or sometimes it really reflects the data quality of your data collection. And statistical difference, it's really used as a quality check by us statisticians. So we always say that the statistical difference, which is it should be less than 5% of your total energy supply, and if it's above, it's too big, it shows that there are some problems, underlying problems in the energy data, either on the supply side or on the demand side, and needs to be investigated. But sometimes a zero statistical difference is also suspicious, because it's very hard to have perfect data. And so a zero statistical difference, it also makes you think that maybe some data points have been estimated to fill the gaps. and might not reflect the reality. So I hope that I have given you some points on statistical differences. There's a lot more that is said in the statistics manual, and yeah, there's a lot on it that can be said, but I hope that I have replied to this question.
Okay, thank you,
Yeah,
Zakia.
please
Maybe as
put
I
questions in the Q&A box. Yeah.
Yeah, of course. We will break again for Q&A at the end. So if you have more questions, both on statistics and modeling, please continue writing them down. And now we will go through the modeling quiz questions and answer all your questions at the end. Zakia, can you just confirm that you can see well my screen?
Yes, it's good.
Perfect. Thank you very much. So still using the Menti platform, I will now propose to you several questions related to energy modeling. But before doing that, I just want to emphasize again that we cannot do modeling, we cannot look at the future, try to anticipate future energy trends if we don't have a good understanding of yesterday's and today's situation. So statistics are really the backbone of any modeling and projection exercise. That being said, let's start with a first question, which is not related to energy, but more to a socioeconomic driver, which is demographics. As we discussed, if we want to look at the future, we will try to think of key parameters that will influence future energy demand and future energy systems characteristic. And one of them is demographics. And here the question you are asked is to find where is Africa out of those three bars. So which bar is Africa? And considering that this figure is showing the number of people that will be added to the urban population between today and 2040. So you have three bars between 300 and 600 million people in terms of urban population growth. Which do you think is Africa? Okay, I can see that your votes go either to the red or the yellow bar. So somewhere between 350 and 600 million people between now and 2040. Okay, we have a perfect equality. So the answer is Africa is the red bar, and I will show you here this dynamic. The yellow bar was the growth in urban population in China between 1990 and 2010. And the purple one is the expected and projected urban population growth in India for the coming 2 decades. So what that mean is, according to UN population and key institutions looking at population and demographics, we expect close to 600 million people in Africa to be born in or to move to cities. And this is of interest to our modeling exercise for the energy sector, because as cities are expected to grow, we expect demand for cement, for building materials, but we also expect more demand for end use, such as powering appliances in the buildings, such as mobility and transport, etc., etc. So this key socioeconomic driver will be very important when we try to anticipate future energy trends, and it's really at the base of the energy modeling. So now one other question where you are asked to find which country is South Africa. So here you have three figures. For each of them, you can see the primary energy demand broken down by type of fuel. you have some historical data. You have the year 2010 and 2018, and then you have projected data for 2030 and 2040. You can see that for each figure there is a different scale, which is expressed in million tons of oil equivalent, and that will vary depending on the figure. And you will see again this different breakdown in terms of fuel. So the question is, which of those three profile is South Africa? And to identify or to find it, you may think of today's situation. You may think of expected evolution of the country. So do we expect an important increase like we have for number one or for number two? Or do we expect for South Africa that the total primary energy demand would remain stable? Do we see a very strong share of bioenergy, the green bar, or do we have a strong share of coal in South Africa, etc., etc.? These are questions that can guide you and help you find the answer. So most of you are voting for the number 3. Maybe another indication is that the legend is not the same everywhere. So here you would see that on number 3, today's and the projected primary energy demand is at somewhere like 130 million tons of oil equivalent, whereas for number 2, today's situation is at 15 MTOE, and number 1 is at 45 MTOE. So this can give you an indication of the order of magnitude of the energy demand of the country. So you're voting mostly for number 2, where we would have more than a doubling. We would have more than a doubling between today and 2040 of the primary energy demand. The right answer is actually South Africa is number 3. A few information backing that is that South Africa has already a very much developed level of primary energy demand, and we don't expect this level to increase, but more to remain at its current level, a bit under 150 MTOE. Whereas for Angola, we expect a doubling by 2040, and we also expect for Ethiopia a very strong increase by 2040. You can see then that in South Africa, there is a very strong share of coal due to the local resources and to the share of coal in the power mix, in the electricity generation. Whereas in a country like Angola, you have a very strong share of oil, because Angola is an oil producing country and is heavily supporting the use of oil in the country for transport, for example, but also for backup diesel generator for electricity production. And in Ethiopia, you have mostly in rural parts a very strong use of biomass, primarily for meeting cooking needs. These are projections under our steps or stated policy scenario, meaning that we are considering what is to happen if the current policies are implemented and under current trends. So one more question. Now you are asked to find where is Ghana amongst those 3 proposals. So it's exactly the same figure with primary energy demand, and you are asked to find which one is Ghana. So I'm sorry, you are meeting the legend, so I can comment again for you. Red is oil, purple is natural gas, blue is hydropower, yellow is solar PV, and green is biomass, bioenergy. Okay, so you're mostly voting for number 1 or number 2. No, number 1 is winning, which would mean that today in Ghana, the share of oil is already accounting for a big share of primary energy demand, and number 2 energy would be bioenergy. Let's have a look at the answer. So indeed, Ghana was number 1 with today a diversified mix, but oil being number 1 and bioenergy number 2 fuels. In the future, we expect the share of oil to increase significantly, but also the big rising energy would be natural gas based on the local available resources. The other countries that were proposed are Ivory Coast, the neighbor, which has a similar energy mix, but a very stronger share of bioenergy as compared to Ghana, and then DRC, where 95% of primary energy is met by biofuels and bioenergy, mostly for cooking needs. And then we have also, you can see a strong share of hydropower, which is the blue bar, due to the very strong hydropower capacities and some dams which are installed on the Congo River and the entire basin. Okay, now we'll try to think of the different scenario we can make when we do energy modeling. You might remember that we have discussed how to make scenario and what is there behind one scenario. So we have discussed two main scenario, one which was steps or stated policy, which is projected, announced targets and current trends. And another one we discussed for Sub-Saharan Africa was the Africa case, which underlying assumptions are, number one, a higher economical growth and inclusive economical growth as per the Africa Union 2063 agenda. Number two assumption for Africa case is universal access to electricity and universal access to clean cooking means. And number three was reduced pollution and reduced emissions to reach climate goals. So here the question is, which of those two projections for Sub-Saharan Africa is under the Africa case scenario? So is it for number one or for number two that we are projecting the Africa case assumptions of universal access, of higher GDP, and of reduced air pollution? Okay, so you're mostly voting for number two, and this is indeed the case. Africa case is on the right part. You can guess it from the higher GDP, which is on the right axis of the figure. You can deduct it by the lower share of bioenergy. This comes from the fact that giving universal access to clean cooking means moving away from traditional use of biomass and then reducing the share of bioenergy used in sub-Saharan Africa. You can also see that there is more electricity generation sources such as solar PV and hydro, which will be required to generate more electricity and to give access to electricity to all the population. And you can also see that there are also a strong increase in gas, in oil, to fulfill the needs for more energy services, for more inclusive economical growth, more transport, more power generation, and more gas as an entrant to the industry as well. But one very strong message you can see here is that under this Africa case, Africa could power an economy which is way bigger with way less energy. If you compare on the stated policy scenario, you see that primary energy demand is above 800 MTOE and GDP is at $10 trillion. On the contrary, in the Africa case, the primary energy demand is below 800 million ton oil equivalent, but this lower energy demand is actually supporting a stronger economy of almost $17 trillion. And this comes from efficiency efforts and improvements that can be done all across the energy system. Okay, now we have one question on the different fuels. So you are asked to find which color is associated with which fuel, and you will be proposed all the fuels we discussed. So coal, oil, gas, solar PV, hydro, and others, and also traditional use of biomass. And if we look at this figure, actually it gives the evolution between a date and a previous one in the energy mix. So looking at the left, you can see China, and this will show you how between 2005 and 1990, the energy mix has evolved. And you will see that the number 6 green bar is a decrease. So the value in 2005 was lower than in 1990 for this specific fuel, but for all the other ones, it was an increase, and you will see by which amount on the figure. Likewise, for India, you would see how the energy mix has evolved between today and 2000. And then on the right part, you will have Africa under two different assumptions. The set of assumptions underlying the steps scenario and the one underlying the Africa case scenario. So here, the question you can ask yourself is, starting, for example, with number 6, this green bar, what fuel do we expect to increase in the steps scenario in Africa, but to decrease significantly in the Africa case? Would that be oil? Would that be gas? Would that be bioenergy? Which can it be? Then looking at number 5, you can ask yourself which source of energy has significantly grown in China, but also in India in the past. What could be this gray bar? Would that be solar PV? Would that be coal, etc.? So I let you some time to try to associate each number with the dedicated fuel. Okay, so we are receiving some first answers. Number 6, according to you, is biomass. Number 5 is coal. So coming to Africa, you can again ask yourself on the light blue or number 2 energy source, which do we expect to grow way faster in the Africa case as compared to the steppes scenario? Okay, so I show you the answer to that question. So the green number 6 one was biomass, and you can deduct it by the fact that in China biomass use dropped, or by the fact that in Africa, in our Africa case, we would have less use of biomass because of people moving away from traditional use of biomass because they gain access to clean cooking. Then number 5 in gray was coal. And as you know, China and India have much developed their energy system and powered their economy in the past decades, thanks to coal and coal-fired power generation. Number 4, or brown, was oil. And you would see that for all those regions and in all the scenario, we expect a rise in the use of oil to meet higher needs for transport, mostly. Number 3 was natural gas. Number 2 is renewable, and we expect in the Africa case for Africa a stronger need for renewables, mostly to provide access to electricity to the entire continent. So this was just a question to think of evolution in energy mix in different regions. Okay, moving to another question, and still thinking of the difference between two scenarios. Here you can see on this figure final energy consumption projections in two different scenarios. So looking at the left part, you would have the picture for fossil fuel, and on the right part for electricity. You have historical data from 2018, and then you have projected data for 2040 under the steppes scenario and under the Africa case. And what is highlighted on this figure is the difference between steppes projection and Africa case projection. And you have in purple some upward changes, and in blue you have some downward changes. The question is, what parameters could be behind the upward changes? So what could lead to the increase in energy demand between those two scenarios, and that would be behind the purple bar. And you have several proposals. Can more energy efficiency lead to an increase in energy demand? Can higher GDP do that? Can lower urbanization or more people with energy access be an upward parameter to those future trends? So this type of figure are very useful when you want to show results of some modeling exercise and to highlight your underlying hypothesis. So here we will very clearly see between one scenario, which is steppes, and the other one, which is Africa case, what assumption would lead to higher energy consumption and what assumption would lead to reduced energy consumption. So you are mostly voting for more people with energy access as a parameter that can drive more energy demand. as well as energy, as higher GDP? Let's look at the answer. So indeed, in the purple bar is made of higher GDP, because we expect that higher GDP will drive more energy consumption, as well as higher energy access. As we said in our Africa case scenario, we have universal access to cooking and to electricity. And on the contrary, efficiency gains is something that will contribute to reduce the consumption of energy. So, for example, looking at fossil fuels, here we have our level of projected demand for fossil fuels in the steps. If we have hypotheses of more people gaining access to clean cooking and using LPG, this will entail an increase in the demand of oil products. But if in the same time we have stronger assumptions that, for example, the cars will be more efficient and on average cars in the country will consume less oil, we have a downward trajectory, which would mean that our final and updated predicted data would be above the one in the steps, but the growth in energy demand is limited thanks to efficiency gains and efforts. Okay, one more question now, looking at the transport sector. So if you think of policies that can be implemented by your government in order to limit or to curb the growth of oil demand from the transport sector. This reflects to one exercise we have done together on Excel, where we have projected how passenger kilometer would increase and then how oil demand would increase, looking also at average fuel consumptions. So here the question is, as policymaker, what parameters can you try to influence if you want to limit the level of increase in oil demand? So you're heavily voting for efficiency of cars, average age of car fleet, and indeed, these are the most obvious parameters that policies can influence. Number of passengers per car is also something that could be tackled. For example, in OECD countries, you can have some incentivize for having more people in one car or for doing car sharing. Imagine that if there is a highway which is not free but you need to pay, you could have some price based on the number of people in the car. So this is also an area policy can influence, but the more obvious one are on the efficiency of cars. And this can come by the average age of the car fleet, which can come from, for example, preventing the country from importing very old cars or preventing old cars to be on the roads, or preventing cars which do not reach a certain threshold in terms of emissions to be on the roads. Not many people have voted for passenger kilometer. Maybe I like to remind you what this parameter means, because it's not passenger kilometer is an aggregated indicator, very specific to the transport sector, but also very useful to understand the intensity of the activity, of how much people want to move or to be transported, because passenger kilometers is calculated as the number of cars in the country multiplied by the average distance traveled by one car and by the occupation or number of people in one car. So passenger kilometer would really give a very good indication of the transport need, and behind it, if we manage to reduce passenger kilometers, we will of course have an impact in the demand for energy for moving passengers. Okay, now we will move to the building sector of trying to think of energy for residential sector. So you can see here several energy needs and uses we have in our houses. So we need to cook, we need light, we need hot water, and we also might need cooling services. If we want to make projection on how the energy demand for cooling will evolve, what is, according to you, the best activity variable to look at? For example, we said that for understanding what the need for energy for cooking will be in the future, it's interesting to look at how many people are there in a household. For lighting, the best activity variable would be the size of the houses. What about cooling? So you are proposed several options. Okay, so most of you are voting for floor space per household, and that's indeed a very interesting variable. You're also choosing appliances ownership, or in other words, the number of fans or of AC units we would find on average in each household. So there is no right or wrong answer. The number one parameter we would love to have and to look at would be appliances ownership, because if we know how many AC units there is per household, if we know how many households there are in the country, and if we are able to project those number of AC units, we will get very easily a good indication of what level of energy, of electricity will be needed in the residential sector for meeting cooling needs. But we can also, as an underlying parameter, look at the floor space per household, because depending on the size of your house, you would need more or less AC units, or you will need more or less cooling services. So here, assuming that we have taken as activity variable the ownership rate of AC units as the best or the easiest variable to understand our need for cooling, we don't know how this number will evolve in the future. Let's imagine today we have on average 0.5 AC units per household in Ghana. How can we estimate how many AC units per household will we have in Ghana in the future? This is not an obvious exercise. What we can do is to look for a proxy variable, for example, GNI per capita or income of the households, and try to find a relation between how in other countries and in historical data we have observed that number of AC units per household is evolving as a function of how income of the household evolves. And the question is here is, if we try to make those two variables a function, the one of the other, what type of curve will we get? We would get an inverse curve or an S curve. Oops, sorry. Okay, so it's like it's almost half between inverse and S-curve. So let's have a look at those curves. This is an S-curve, and this is showing the ownership rate of refrigerators, but it could be AC units, as a function of a discriminant criterion. So an S-curve means that as the income, which is in abscissa, will increase, we expect that the number of refrigerator per household will increase too. So it's increasing sharply at the beginning, then it's increasing constantly, and at the end it's stagnating, because even though tomorrow you earn twice as much as you earn today, even though your income doubles, you will not you will not double the number of refrigerators or AC units you have in your place. You reach some saturation as your income increase. You might also remember from this slide that sometimes when we try to identify a function of, for example, the number of AC units in household as a function of the income of the household, we don't have enough information and we need to bring more discriminant criteria. So here you can see that all those dots are not making a clear S-curve, but if you regroup countries based on the weather, you would see more clearly S-curves, because of course, if you are in a country like Norway, where it's very cold, even though you have an increase in the household income, you will not see an increase in the number of air conditioner, because this is not a service which is needed. But if you look at countries in red, where the annual cooling degree days are higher, meaning that you have hot weather and stronger needs for cooling, you can see that as income of household increase, the rate of ownership of air conditioner is also increasing, and here we can find our S-curve. You can see it again with a different criteria, but the idea is always to consider that we don't know how many AC units people will have in the future, but we can know what happened in similar countries in the past. And if we are able to make projections on how GDP per capita will evolve in the coming 10 years, we can deduct how AC units ownership could evolve based on this evolution of income. Okay, some more questions, and now we are moving to the power sector. So here again, you will see historical and projected data of electricity generation mix. And you will have the breakdown by source of electricity generation. The question here is, according to you, which country is Ethiopia? Is it number one, where you can see today a very strong share of gas? Is it number two, with a strong share of hydro, which remains strong in the future? Or is it number three, which something very diversified and also an important part of geothermal as a source of power generation? So far, you're mostly voting for number two. Hydro may be indeed a good parameter to look at. You may be aware of the Great Renaissance Dam in Ethiopia, which is under construction, and that would be a giant hydropower dam of I think something like 2 gigawatts of installed capacity for electricity generation. Okay, so you're mostly voting for number two, and that's indeed the case. Number one was Côte d'Ivoire with a lot of gas fired power generation. And then in Kenya, you can see that Kenya is really leading the way in terms of using geothermal sources for electricity generation. But Kenya has also a very diversified mix with hydro and with solar PV. These were today's situation. If you look at projections, you would see that in all countries we expect solar PV to rise significantly. Okay, same question, but now trying to find where is Ghana. I'm sorry that the legend is again missing, but I can tell you verbally. Red is oil, purple is gas, dark blue is hydropower, clear blue is wind, yellow is solar PV, and green, I think, I can't recall what's. So here you have two countries which have a similar level of electricity generation. You can see that today we are below 20 terawatt hour generated, and we expect it to grow to double to 40 terawatt hour by 2040. In one case, we have oil as a source of electricity generation today that would remain at almost the same level or increasing. But in the number one, we can see gas increasing a lot. It increases as well in number two, but for number two, hydro is the main source of power generation. Okay, so you're mostly voting for number one. And Ghana is indeed number one. Number two was Mozambique, with a very important share of hydropower. You can see that in our projection, solar PV is increasing very fast in both countries to come in the case of Ghana at somewhere below 10% of electricity generated by 2040. Okay, a question more technical and related to electricity demand. So here you can see annual hourly demand for electricity for two countries. So you would see that on the left, we are starting at January 1st, the first hour of the day, and we are ending with the last day of the year, December 21st, which is the hour number 8,760. And you would see that the electricity demand is evolving, and you can see some seasonal patterns, meaning that you would have some seasons where electricity is lower and seasons where electricity is higher. So we have countries that we call winter peaking, where electricity is higher or is peaking during winter, and we have countries where electricity demand is peaking in summer. So here you are asked to associate which is a winter peaking and which is a summer peaking country. Just as a comment, this concept might be pretty northern, because as you would know, in Europe, for example, we have seasons which are very strong. The temperature difference is high between winter and between summer. So this reflects in very different behaviors. Whereas in tropical areas or countries like Ghana, maybe there are no such differences. I would assume there are some wet or rainy seasons and seasons which are drier, but you might not have such a strong temperature difference that would reflect in very strong differences in energy demand profile. Okay, so you are mostly associating number one with winter peaking and number two with summer peaking. Actually, that's not that's the case indeed. In number one, you can see that in the northern winter, so in December and January, we have higher electricity demand because there are more needs for space heating. And number two country might be, for example, Italy or Spain, which is a warm country, and during summer it's very hot, and there is needs for electricity for cooling. So the main parameter would be whether you need heating or cooling, and this would reflect very strongly in electricity demand. And when you look at hourly electricity demand data, you can see several patterns. You can see changes in electricity demand. So between seasons, as we just said, in winter, you might need a lot of electricity for heating. And in summer, in Europe, in summer, the day will last longer. So there is less need for lighting, for example. There is no need for heating. So you would have a lower electricity demand. Then you can look month after month, and you would see some patterns in terms of working days. So for example, here you would have Monday to Friday, and then during the weekend, you have lower electricity demand. And even when you look at one day, you will see that there is not the same demand for electricity depending on the hour, and you would identify daylight hours high consumption time versus night low consumption period. Okay, one more question still on electricity demand. If we look at historical and projected data of electricity demand in or reflected in the installed capacity, here the red line is electricity demand, knowing that between red and yellow you have what we call the peak to average ratio, where which line would be the total installed capacity? Would that be the yellow or the blue one? Okay, you are 50-50 voting. I will quickly show the answer. So if red line, you would have historical total electricity demand, and then you will project it in the future years. This is the average annual demand, but what we need to take into consideration is the difference between the average and the peak. As you remember, when it's 6 p.m. and when it's a time when people are demanding more electricity because maybe it's winter, it's cold, they need to heat their home, or it's summer, it's very warm and they need to cool their home, we will reach a peak which is above the annual average. And we need to take into account this peak, and we need supply to be able to match at any time this peak level. And then we also need to take some capacity margin or reserve margin to deduct what the level of capacity needs to be, because we might have some power plants that will require maintenance operation at some time. So if we want supply to be at any time at the exact same level of demand, we need installed capacity to be above the peak demand value. So this is why you see moving from demand to peak demand, and then from peak demand to total installed capacity, taking into consideration peak to average ratio and some margin for capacity. Okay, this is the last question, moving to oil and gas operations. So here you can see for oil and for natural gas, the CO2 emissions, the the greenhouse gases emissions related to the production of oil and natural gas. As we all know, those operations are intensive in terms of emitting greenhouse gases emissions, but we can decrease and we can reduce emissions. And there is one parameter that can really heavily contribute to a decrease in emissions. Here you can see that it's in dark blue. And the question is, what is that parameter? Would that be reducing CO2 flaring? Would that be tackling methane? Would that be tackling CO2 venting? Or would that be reducing the CO2 emissions from the own energy use? Which of those four parameters would mostly contribute to reducing the emissions of oil and gas operations? Okay, so I see a bit of all the answers, but you're mostly voting for the CO2 emissions from the own energy use and the flaring of CO2. And indeed, CO2 flaring and CO2 venting, for example, have been for a long time under scrutiny of oil and gas operators as an important parameter to take into account in order to reduce CO2 emissions. But increasingly, what we see is that methane is really a low-hanging fruit, meaning that there is a very strong potential to reduce emissions intensity of oil and gas operation if we reduce methane leaks, if we reduce methane emissions under the production process and the operations of oil and gas. Then would come energy-related CO2 for oil, and then flaring and venting of CO2. Okay, so this was the last question of our quiz. I want to thank you very much for your participation to this. Of course, all the questions asked are referring to topics we discussed during the course and that you can always access using the video recordings or looking at the presentation. So, oops. So we are done with our online course. I just like that we take with you, Zakia, 5-10 minutes just to close this online training, because we've been through 12 webinars over the past 3 and 4 weeks. So we would really like to thank you for your participation, for your attention. We would like to remind you that all the material that we presented to you is available online, that the video recordings are available, that we remain at your disposal if you have any question. And I would also like to give the floor to Mr. Jafaru from ICRI, who has helped us identify some key participants from Ghana, but also from neighboring countries under the ECOWAS region. But I'm not sure Mr. Jafaru is still with us. Okay, maybe in the meantime, Zakia, I don't know what you think. Maybe we can discuss the next steps, and if Mr. Jafaru connects back, we can give him the floor so that he shared some thoughts with all of you. I'm sorry, Zakia, I can't see you because I don't have the video. I don't know if you're here.
Yeah, I'm here.
Sorry.
Yes. So thank you everyone for listening to us for the past 2 weeks, and we really look forward to continuing the collaboration with many of you regarding statistics, especially. We'll stay in touch as we improve our data collection on Ghana, and we will also be organizing some bilaterals with many of you who are experts on energy prices and energy efficiency indicators, and we will be getting in touch soon to organize those meetings and see how we can work together to produce those indicators and data which are so important for policy making and better knowing what is available. Um, I think we have our colleague from ECRI who joined us.
Oh yes, that's sounds like we Jefferu is back. So Jefferu, thank you very much for joining. As we mentioned, this online course has been organized mostly for Ghana, and I first would like to thank Mr. Anthony Dadra, who I think is not in the call today, but who has been our main focal point, and who has really helped the organization of this online course. So he was our main supporter and organizer for this activity from the Ghana Ministry of Energy. But we have also been very happy to involve and to collaborate with ECRI, so the ECOWAS Center for Renewable Energy and Energy Efficiency, and we have been very happy to have in this online course a few participants from other countries of the ECOWAS, Cabo Verde, the Gambia, Sierra Leone, and Liberia. And I would like to give you the floor, Mr. Jafaru, if you can share very briefly how ECRI is also working on energy data in the region, and yeah, share a few thoughts on the importance of this type of training on energy statistics and modeling. So the floor is yours, Jeff.
Okay, thank you, Arnold. Thank you very, very much. Thank you, Zakia. Um, Distinguished participants, my fellow colleagues, I'm sure some of you are familiar with ECRI's activity, but I just want to say on behalf of the Executive Director, I wish to congratulate you all for this successful training, and also for we have express our sincere gratitude for your participation. Um, we want to thank the IEA for this initiative to organize these events in various countries in West Africa specifically. And I hope we will all benefit from this experience, and as well as apply it in our various institutions. No doubt the importance of this training is very, I mean, it's very, very clear. I don't have to stress more. We know the only way to move this sector forward is by engaging in data management, proper data management, so that we'll be able to see how we progress timely. I want to assure you of ECRI support and partners as well. And I would like to use the floor, just like Arnold said. Um, Over the years, ECRI has been engaged in so many ways with various partners, various body, government, private bodies in terms of standardizing energy data in the region. Um, I just one of such initiative is uh, the statistics we collect annually to monitor our progress towards achieving our regional targets. So at the moment, this is one of our flagship projects in which we yearly engage in statistical data. Um, as we are all aware, in 2013, we had our regional energy efficiency and renewable energy policies adopted by the heads of state.
We have some connection problem.
Yeah, I'm afraid we're losing Jafaru. Okay, let's wait 10 seconds.
Yeah.
Were able to develop their national action plans. So at some point we realized that in terms of data collection statistics, it's very poor and we cannot monitor the progress made by the member states. And then together with the member state, we came up with a template for elaborating a reliable and energy annual reliable statistics that will feed us with useful information on the roadmap towards achieving our regional targets. So this is, at the moment, this is what we are doing to engage the member states. This is very, very important because whatever we're doing is tied down to our policies that we have made ourselves. So it is very important that at the end of the day, we are able to see how far we have gone. If I point out in short, so far we see that the target set for 2020, we are nowhere to achieving those targets. And that is good in the sense that we are aware of that and we will put more effort during the coming years in order to see how we can meet our 2030 target. So just in summary, I must say this training, when we had a discussion with our colleagues from IEA, we find it very, very important and useful. And like I said from the beginning, we hope this experience will go a long way towards supporting you in carrying out your daily tasks within your institutions. And as well, ECRI is always there to support. We will, I'm sure some of you are also engaged in our data collection. We will be reaching out to you, and I hope this training will aid in how you develop and manage your energy data statistics so that we can together forge ahead in terms of moving the sector forward. So once again, on behalf of the EDA, I thank you all for participation. And we hope to see more of this from our partners from IEA. I see there are quite a few training which are planned. And once again, thank you very much, Arnold, and your team for this wonderful training. Thank you very much.
Thank you very much, Jafaru, for being with us, and thanks for the collaboration with IEA. As you highlighted, I think we all aim to create more synergies, to collaborate more. We would like to make sure that as much as possible, you as energy professional in Ghana and in other countries, you can share and report your national statistics maybe to one only partner. So we'll aim to collaborate as much as possible between ECRI, IEA, and other partners.
Yeah,
Thank you.
thanks a lot.
Thank you.
So maybe we can go back to this planning and organization. So yes, so as you just saw, we are still in phase one of the project. where we just did the full online training, which is 24 hours. And this has been all virtual because of the pandemic situation. But we are hoping that in phase 2, we will be able to travel. So for today, as we are closing the online course, please fill in the survey and help us improve it. You will be receiving the evaluation survey by email. And at the end of the session, we will also be sending out diplomas in the coming weeks to all participants. And we will stay in touch with all of you through the different activities that we will be organizing. There is the IEA Africa universities every month, where we present to you flagship publications of the IEA and our key findings. And we will be having also face-to-face activities soon in phase 2. There is also the linking group, and where we try to stay in touch with our community of African energy practitioners, and you will be able to exchange also with other countries which are in the program. And there is the continuous collaboration on energy data through the bilateral meetings that we will keep organizing, and that my team in Stats, we organize on the data. So if you have questions, technical questions on Ghana energy statistics, we can look at this together. And we will also be looking deeply on energy prices and energy efficiency indicators, where we will have bilateral meetings as soon as possible. Then in phase 2, which we are hoping to start from next year, hopefully, there will be the in-country practical session, where we are hoping that Arnaud and I and other colleagues will be able to come to the country and for a few days, where we will do some practical work and more country-specific exercises. We will also be able to look at some of the training sessions where you want us to deepen more. There will be also a practical project which we are hoping to build together on either modeling or statistical tools, and that would last for a few weeks, where you will have remote support from IEA experts to work on a project that you want to develop. And we will close the project with a project restitution and more training events, hopefully maybe in Paris this time. And yeah, so additional trainings which at the IEA we will be organizing. So this is more or less the big plan of the project, which we will adapt again according to the situation. And this is the team that the IEA team that has been working with you over the past 2 weeks. And so there's the teaching team with me, Arnaud, and Marina. And again, for Marina, if you want to join our linking group and have not yet done so, please send her an email, and she will add you to the group. And then you have the teaching experts of the different people who have joined the different sessions over the course of the training. And again, do not hesitate to write to any of us anytime, even in a few weeks, in a few months' time. We are here ready to help and help you progress in your data or modeling development phase. Thanks, everyone. And I don't know if you have anything else to add.
No, thank you. I just want to thank again all the participants for your attention. And this is not the end, but the beginning of our collaboration. So as Zakia mentioned, we are happy to answer any question per email, to continue to be in touch, to provide information, to meet you in the monthly IEA University. So you have our contacts, you are aware of the activities we are organizing. So we really look forward to continuing the collaboration.
Yeah, and there's also the WhatsApp group that is that will continue to live, and we can also stay in touch there.
Okay, so thanks
Thank
to
you.
everyone. Thank you, Zakia. Thank you all, and have a very
Thank
good
you.
day.
Bye.
Okay, bye-bye.
Thank you.